Hidden within these seemingly ordinary stones can lie one of the rarest and most valuable gems on Earth, a blue diamond. The tragedy is that without knowing what to look for, the average person wouldn't even think to crack one open. The first signal isn't color or sparkle, it's weight. These nodules often have a denser than expected heft when lifted, betraying a mineralogical complexity that isn't visible from the surface. That extra weight hints at heavy accessory minerals, chromite, ilmenite, or even diamond-bearing matrix, often embedded within the rock's fine-grained structure. In the field, this weight-in-hand test is subtle but surprisingly telling, especially when you've handled dozens of similar-looking stones in the same area. Next, the surface texture plays a role. Kimberlite, one of the few volcanic rocks known to transport diamonds to the surface, weathers into a dull gray-green crust that may look like nothing more than hardened clay. But it often contains tiny, rounded grains or angular fragments, called xenoliths, of mantle material. When weathered, these grains can leave a stippled, pockmarked pattern that's easily overlooked unless you're examining closely with a 10x loupe. A light rub with water may reveal subtle differences in sheen or inclusions that don't belong in sedimentary rocks. In riverbeds or alluvial fans, these nodules are sometimes partially buried among quartz-rich gravels. The temptation is to dismiss them as just another cobble. But when found alongside heavy black sands, magnetite, ilmenite, and garnet grains with a pink to deep red hue, they're worth immediate attention. These associated minerals are crucial. Their presence strongly correlates with the erosion of diamondiferous pipes upstream. In fact, professional prospectors often chase these accessory minerals far upstream to locate the original kimberlite pipe. Most hobbyists never get to this stage because they skip the basics. They don't open these rocks. Yet inside, visible only once split with a rock hammer or cut slab, may lie a bluish crystal nestled in a carbonaceous matrix. If you're extremely lucky, that blue glint isn't corundum or a dyed simulant. It could be a type IIB blue diamond, the rarest and most chemically pure of all. What sets a valuable host rock apart isn't its shape or size. It's the subtle interplay of weight, luster, and fracture that reveals its hidden potential. Most untrained eyes scan riverbeds for brightness, mistaking shine for value. But in diamond hunting, the early clues often present in matte surfaces with peculiar resistance under the hammer. A nodular rock that doesn't shatter like shale, but breaks unevenly with fibrous or granular resistance, deserves scrutiny. Start with luster. True kimberlite or lamproite can show a greasy to slightly waxy sheen when freshly broken, especially if it contains serpentinized olivine or carbonatite streaks. It won't gleam like quartz, but has a damp, organic dullness, reminiscent of soapstone. Under magnification, embedded crystals, if present, may reveal more, some octahedral, others rounded, and in rare cases, hinting at cubic outlines. This habit is not proof of diamond, but suggests the host matrix cooled under high pressure, a requirement for diamond survival. Color isn't decisive, but it's worth noting. While many nodules are greenish-gray, others lean toward bluish-gray or brown, depending on weathering and mineral content. A bluish tint can indicate phlogopite mica, often found in diamond pipes, or even trace amounts of chromium. Still, color alone misleads. What matters more is context and accompanying minerals. The next test is weight in hand. On average, a dry baseball-sized granite rock will weigh around 1.5 to 1.8 kilograms. A similar-sized kimberlite nodule could push 2.2 kilograms or more. This density difference comes from the inclusion of heavy minerals like ilmenite, Sg 4.7, chromite, 5.1, and even diamond, 3.52. While you won't detect tenths of a gram without a scale, field experience builds intuition, especially when samples from the same stream differ sharply in heft. Fracture behavior is another giveaway. Kimberlite often breaks irregularly, but with sharp, planar breaks where it encapsulates harder minerals. A hammer strike might pop out small, rounded garnet grains or shiny black fragments. These aren't just curiosities. Garnet type matters. Pyrope garnets with a deep violet-red hue are key indicators. If the fragment is magnetic, it could be magnetite or ilmenite, both common in diamond differ systems. Perhaps the most overlooked feature is the presence of reaction rims. Tiny halos of mineral alteration that form when mantle materials react with ascending magma. These can appear as faint zoning rings around embedded grains or color gradients within the host rock. Under a loupe or field microscope, they suggest the rock hasn't just undergone pressure. It's been through a geologic event capable of transporting diamonds from 150 plus km depth. These traits may seem subtle, even unreliable in isolation, but collectively, they define whether a rock just looks the part, or whether it might actually contain a stone worth breaking it open for. Yet even promising rocks can deceive. In the next topic, we'll follow how their journey across terrain holds the key to tracking their true origin and ultimate value. A diamond-bearing rock is rarely found in place. Most of the time, it's a traveler, a fragment broken from its volcanic source and carried across kilometers of terrain by ice, water, or time. Understanding where these rocks come to rest is as crucial as recognizing their traits. The map beneath your feet may hold the secret. A convergence of paleochannels, ancient volcanic vents, or glacial spill zones. All potential highways for diamond migration. The source itself is ancient. Diamonds form deep in the mantle and are only transported to the surface by violent eruptions of kimberlite or, less commonly, lamproite magmas. These events are millions to billions of years old. What remains at the surface today are often eroded remnants of vertical pipes, typically circular in aerial view and measuring from 100 to 2,000 meters in diameter. Most are deeply weathered, covered by laterite or forest, and not obvious unless mapped geophysically. But while the pipes are fixed, the diamonds are mobile. Glaciation has scattered nodules across vast territories in Canada, Russia, and parts of Scandinavia. These erratics often settle in terminal moraines or beneath till sheets, far from the original kimberlite pipe. That's why the best discoveries come not from the pipe's edge, but from its erosion pathways. In drier zones, Botswana, Australia, India, wind and water play that role. Seasonal floods and alluvial fan systems push fragments downslope and into secondary stream beds, sometimes concentrating heavier materials in placer-style deposits. These systems tend to form in braided streams or ancient meandering rivers that have long since dried up, leaving behind gravel bars rich in indicators. Modern prospectors rely on 3 geological clues to chase these hidden channels. 1. Magnetic anomalies, since many kimberlites are rich in magnetite and show up as bullseyes in airborne surveys. 2. Gravity lows, because weathered kimberlite is less dense than surrounding country rock. And 3. Indicator dispersion trains, long arcs of ilmenite, garnet, and chromite that point upstream to the source. Even without high-tech gear, you can read the terrain for signs. Look for inside bends in streams where heavy sands settle, or depressions in floodplains that collect fine material during runoff. Erosional gullies cutting through basalt or craton edges are especially promising. These are natural traps for migrating stones. Elevation plays a role too. Diamonds move downhill, but so do many other materials. Rocks caught in perch terraces or colluvial fans are often overlooked, yet they may represent older deposition events, capturing diamonds before they were flushed farther downstream. Finding a diamond in the field is statistically rare, but finding the minerals that travel with it is not. These indicator minerals are geologic breadcrumbs. They survive erosion, resist chemical breakdown, and settle in predictable ways that lead directly to the source. Among them, a few names dominate the diamond hunt: pyrope garnet, chromite, ilmenite, and in more complex pipes, clinopyroxene, and spinel. If these show up in your pan, sieve, or concentrate, you're no longer guessing. You're closing in. Pyrope garnets are the headliners. Their deep purplish red to violet hue separates them from the more common orange almandine garnets. But it's not just color, it's chemistry. Pyropes associated with diamonds often contain elevated chromium and low calcium. In the field, though, you can't run a lab scan. What you can do is look for a particular glassy luster, sharp dodecahedral faces, and unusually high density. If a garnet resists scratches from steel, hardness 7, and sinks quickly in water, it's a candidate worth isolating. Chromite and ilmenite come next. Both are opaque, black, and heavy, but telltale differences exist. Chromite often has a submetallic luster and a high specific gravity, 5.1, and under a magnet, it may show weak attraction. Ilmenite, slightly lighter, 4.7 Sg, is typically more strongly magnetic and has a duller, iron-black surface that sometimes shows oxidation rims, tiny rusty halos. Sweep these rocks with a simple neodymium magnet over a pan or sheet. Fragments that shift or jump slightly warrant collection. Then there's spinel and clinopyroxene, more elusive, but still useful. Chrome spinels are tiny, black, and subhedral, while clinopyroxenes may show pale green to brown hues with subtle cleavage patterns. These minerals help triangulate pipes that have already eroded. Their presence, especially when found downstream of other indicators, marks a strong target area. These minerals don't spread evenly. They form what geologists call dispersion trains, elongated trails of mineral fragments carried by water, ice, or wind. A single stream sample might hold 5 garnets, while the next upstream only holds 2. Follow the concentration gradient uphill or up ice, and you move toward the source. Smart prospectors grid these patterns meticulously, sometimes over years, before ever cracking a rock open. One pitfall: zircon. It's heavy, 4.6 Sg, hard, 7.5, and can appear with all the right indicators. But unlike pyrope, it often comes in transparent golden or reddish crystals with resinous luster. While valuable in other contexts, zircon is a frequent false positive in diamond exploration. It takes less than a minute to run, and it can change everything. The magnet sweep, followed by close visual analysis under a 10x loupe, is the prospector's first serious filter in the field. It doesn't prove a diamond is present, but it flags the rocks and concentrates that might justify breaking open or sending for further testing. And in the best cases, it reveals key inclusions hiding in plain sight. Start with the magnet. A strong neodymium magnet, small enough to carry in your pocket, but powerful enough to tug through soil, is essential. As you pass it over a sieved concentrate or even a fresh rock surface, pay attention to the reaction. If fine black grains jump or shift, you're likely looking at magnetite or ilmenite. These aren't diamonds, but they often co-occur in kimberlitic contexts. The real value is in their presence alongside more subtle signs. In rocks, a magnetic tug suggests embedded ilmenite veins or disseminated grains. Strike the rock to expose a fresh surface. Use your loupe to scan for minute black blebs, tiny spherical or angular inclusions, contrasting against the greenish or gray matrix. Their shape and location matter. Inclusions aligned along flow bands suggest a volcanic origin, which strengthens the case for kimberlite or lamproite. After the sweep, switch to dry panning or sieving. Use a number 20 mesh, 0.85 mm openings, to isolate coarse fragments, then recheck the concentrate under the magnet. For samples with higher proportions of heavies, step down to a number 40 mesh, 0.425 mm. To resolve finer grains like garnet or spinel, wet the concentrate and swish in a battue pan to further separate light from heavy. True indicator minerals will settle rapidly and resist current. Now bring in the loupe. Under 10x magnification, a pyrope garnet reveals itself by its sharp, dodecahedral crystal form and intense vitreous luster. These aren't rounded river-worn fragments, but angular, high-pressure relics from the mantle. Black grains with metallic luster and weak magnetism point to chromite. Any pinkish or reddish garnet that seems to glow in the light demands retention. One mistake is assuming anything blue must be a diamond. Many non-diamond crystals, including sapphire, glassy quartz, and fluorite, show blue hues but fail under scrutiny. A genuine blue diamond inclusion may be visible through the matrix as a tightly embedded octahedron, faintly transparent with no obvious cleavage planes. But at this stage, it's nearly impossible to confirm in the field. Even promising finds can mislead. An inclusion might test magnetic and show garnet zoning, but still lack any trace of diamond. The UV test was supposed to confirm it. Instead, it introduced doubt. The promising nodule, heavy magnetic garnet bearing, lit up under long-wave ultraviolet with a ghostly blue glow. To the untrained eye, this seemed like a win. After all, many natural diamonds fluoresce blue. But here's the trap. Fluorescence is not diagnostic. In fact, several false positives mimic diamond behavior under UV light, and unless you know what to look for, you risk chasing glass, calcite, or synthetic analogs. Begin with expectations. About 30 to 35% of natural diamonds fluoresce blue under long-wave UV, but not all do. And crucially, the intensity varies. Weak to moderate bluish glow that fades quickly is more typical. If the glow is intense and chalky, you're more likely seeing fluorite or a high-index simulant like cubic zirconia. Calcite may fluoresce red or orange, and some garnets, especially those with manganese content, can emit a subtle yellow-green hue, another potential distraction. The smarter move is to follow UV with a thermal conductivity test. This is the field prospector's secret weapon, especially in the era of affordable handheld diamond testers. Real diamonds conduct heat extraordinarily well, second only to silver and copper. Moissanite, a frequent diamond simulant, also conducts heat, but here's the catch. It conducts electricity, which diamonds do not. In practice, press the probe of a thermal tester against a cleaned, exposed inclusion. If the response is immediate and the device registers diamond, it's worth noting, but not yet celebrating. Run an electrical conductivity test if possible. If it conducts electricity, it's moissanite. If not, the odds lean toward genuine diamond, though other steps remain. One limitation of these field tests is surface contamination. Dirt, moisture, or mineral coatings can interfere with conductivity readings. For accuracy, the test spot should be dry and freshly exposed. Use a diamond file to gently reveal a clean facet, ideally a natural plane or fracture surface. Repeat the thermal test. Still positive? You're inching closer. Another twist. Some natural blue diamonds don't fluoresce at all. These are often type IIB, the rarest and most chemically pure subset, colored by trace boron rather than structural defects. Their lack of fluorescence and low nitrogen content set them apart, but also make them harder to verify in the field. So, where does that leave you? If a stone fluoresces blue, conducts heat but not electricity, and resists scratching from 6 sandpaper, hardness 9.5, it's a strong candidate. But the decision to break the rock, assay it, or send it for cutting still requires more than test kits. It requires a systematic approach. That means sampling smartly, recording precisely, and gridding your search to avoid false trends. Because one hot rock doesn't make a pipe, but 5 hot samples in a cluster? That's worth chasing. Next, we'll map out the exact field workflow that transforms a hunch into a repeatable search pattern. Without structure, the search for diamondiferous rocks is just guesswork. But when you grid, sieve, and document your sampling with discipline, patterns emerge, and those patterns tell you where the real value lies. The difference between a lucky find and a viable source is repeatability. And that starts with field protocol. First, set your grid. Choose a zone based on prior indicators, perhaps a stretch of stream where pyrope, garnet, and ilmenite have shown up, or a glacial till field with magnetic anomalies. Mark out a rectangular area, ideally 100 by 100 meters, divided into 10-meter cells. Each cell gets a sample, and each sample gets labeled, sieved, and processed identically. GPS or flagging tape can help track exact spots, but even a hand-drawn grid in a field notebook is better than memory. Now for sampling. Within each cell, scoop roughly 10 liters of material from the top 20 centimeters of sediment, unless you're in a hard rock exposure. Then chip fragments from the exposed face or float material. Wet the sample in a large pan or basin and pass it through a number 20 sieve, 0.85 millimeters. This removes light organic matter and isolates the coarser mineral fraction where diamonds and indicators tend to hide. If you suspect finer-grained indicators, especially garnet or spinel, step down to a number 40 mesh, 0.425 millimeters, for the same sample. Save both fractions. Let them dry completely, then run a magnet sweep. Use a clean sheet of paper or plastic tray to catch magnet-reactive grains, noting their proportion and distribution across your grid. Next, scan with a loupe. Focus on the heavy fraction. Are you seeing translucent garnets with sharp crystal forms? Black metallic grains? Anything blue or angular that resembles diamond habit? Document what you see, even if it feels inconclusive. After 20 to 30 samples, the spreadsheet tells a story. Indicator counts rise in one direction, disappear in another, or cluster around a terrain feature like a bend or outcrop. Don't ignore float rocks during sampling. A single large nodule showing magnetic tug and garnet inclusions deserves its own analysis. Break it, check for internal zoning, and inspect any visible inclusions with a loupe. Photograph both surface and fracture plane. Even if no diamond is visible, the context matters. That rock's mineralogy can calibrate your expectations for surrounding materials. Labeling and storage matter too. Place concentrates in small sample bags, labeled with grid number, GPS, if available, date, and any immediate notes. 5 garnets, 1 black magnetic grain, for example. Keep dry and separate to avoid cross-contamination. Over time, your grid reveals not only where to focus, but how your indicators behave spatially. The garnets looked perfect, deep violet red, angular and heavy. The black grains tugged at the magnet just enough to suggest ilmenite. Even the host rock had that serpentinized, dull sheen that so often accompanies kimberlite. Everything pointed to a potential diamond-bearing zone. But one test shattered the illusion: specific gravity. The most convincing indicator suite turned out to be a cleverly disguised false positive. And it's not an isolated case. Zircon is the usual suspect, transparent to reddish-brown with an adamantine luster. It mimics diamond's brilliance and heft, clocking in at a density of 4.6, 4.7, high enough to settle with real indicators in a pan. Under a loupe, it may even show sharp crystal faces. But here's the catch. Zircon often fluoresces under UV, is non-magnetic, and critically, shows double refraction under magnification, especially in faceted forms. In the field, without polarized light or a refractometer, these traits are hard to confirm, making zircon a persistent source of confusion. Moissanite is worse. As a synthetic diamond simulant, it not only conducts heat, triggering thermal testers, it also scores 9.25 on the Mohs scale and passes the scratch test. It can only be ruled out by its electrical conductivity, or by spotting facet doubling through a 10x loupe. In uncut or rough form, moissanite may even occur in rare natural deposits, particularly in meteorite impact zones, further muddying the waters. corundum, sapphire, and ruby, is another common misread. While typically associated with aluminum-rich metamorphic rocks, some blue sapphires resemble rough diamonds to the inexperienced. But sapphire's density is lower, 4.0, and under UV, it usually shows little or no fluorescence. Still, many dyed quartz or topaz stones are passed off as blue sapphires or even diamonds in field markets, especially when faceted. That's why host matrix matters. If your suspicious crystal is found in granite or schist, it's likely not a diamond. Glass, of course, is the most deceptive and least valuable mimic. Its luster, hardness, 5.5, 6.5, and shape can mimic rough diamond nodules, especially if river-worn. Colored glass shards, especially from bottle dumps or historical sites, often find their way into alluvial channels. They may fluoresce, scratch glass, and look close enough to fool even semi-experienced collectors. A scratch test with 6 sandpaper, 9 hardness, often eliminates them. They'll abrade, chip, or show conchoidal fracture patterns, unlike a real diamond. Even ilmenite can deceive. In regions with mafic or ultramafic bedrock, ilmenite occurs widely, sometimes with no diamond connection at all. Without accompanying pyrope garnet or chromite, magnetic black sands aren't meaningful. That's why overlapping indicators are essential. A single trait means nothing, but a cluster forms a credible geologic case. After a false positive, the next step is to recalibrate, not abandon the search. Use this moment to refine your criteria. Double-check host geology, look for zoned mineral grains under the loop, and prioritize samples showing multiple co-located indicators. Because while these imposters waste time, they also sharpen your skills for the real discovery. The crystal looked right. Blue, glassy, nestled within a dull green-gray matrix. It had passed the loop inspection and even lit up under long-wave UV with a pale, steady glow. The thermal probe confirmed high conductivity, and it scratched glass cleanly without damage. Every box was checked, until it wasn't. When weighed in water for a specific gravity test, the result landed at just under 2.9. That number changed everything. For a diamond, specific gravity should hover around 3.52. Sapphire, about 4.0. Even glass usually falls between 2.4 and 2.6. A reading of 2.9 suggests something in between. Too light for diamond, too heavy for quartz. Nephrite jade? Possibly. A feldspathoid mineral? Maybe. But certainly not the $50,000 find the prospector had envisioned. This was the moment of reversal. The test that unmasked the blue stone, revealing it as a common synthetic spinel. Often used in jewelry, occasionally found in placer deposits, but never associated with kimberlite. The setback wasn't just a blow to the ego, it challenged the entire grid. If the best sample, collected at the indicator-rich heart of the site, wasn't real, what did that say about the rest? Were all the garnets just calcium-rich grossulars? Was the magnetism due to surface magnetite contamination and not ilmenite? This wasn't a failed expedition, but it was a recalibration point. The key lies in comparative testing. Instead of treating one promising stone as the anchor, multiple samples from across the grid are run through identical tests: SG, UV, thermal, magnetism, and loop examination. Patterns emerge. In this case, the majority of garnets failed the chromium test, green flash under specific lighting, suggesting they weren't pyropes. Ilmenite grains were confirmed, but without the accompanying suite. No chromite, no eclogitic garnet. Their presence meant little. But this wasn't all bad news. The data clarified where not to look. Cells that had produced false positives could be ruled out. Focus shifted to the upstream bend, where multiple grains did test positive for SG above 3.5, and one inclusion passed all tests including a failed electrical conductivity probe, meaning it was not moissanite. This is how a false positive becomes a pivot point. It forces tighter methods, smarter sampling, and reliance on converging evidence rather than hope. In high-stakes prospecting, the goal isn't just to find a gem. It's to build an irrefutable case for its source. And that's why, even after a reversal, professionals double down with established methods and global protocols. Across Canada's tundra, Botswana's scrublands, and Australia's dry interiors, some of the world's richest diamond fields were found not by luck, but by following a suite of standard methods, reproducible, field-proven, and used by government and private survey teams alike. These methods aren't glamorous, but they work, and when followed precisely, they turn a scattered set of mineral grains into a resource-backed claim. The process begins with indicator mineral surveys. National geological bodies, like Canada's Geological Survey, GSC, or Australia's CSIRO, deploy trained teams to collect stream sediment and glacial till samples across broad grids, often spaced kilometers apart. Each sample is sieved to separate 0.25 to 1 millimeter grain sizes and analyzed for key indicators: pyrope garnet, ilmenite, chromite, and chrome diopside. Not every find matters. It's the concentration, collocation, and chemistry that count. After collection, grains are subjected to microprobe analysis, often electron-based, to determine precise compositions. Pyropes rich in chromium and low in calcium are flagged as G10 or G9 garnets, both considered highly favorable for diamond association. Ilmenite is tested for magnesium content and oxidation state. Only certain chemical variants are tied to diamondiferous kimberlite. Chromites are analyzed for CR, Fe ratios. These chemical fingerprints narrow the field dramatically. In many national surveys, results are fed into GIS systems to build dispersion models. If 3 or more indicator minerals with favorable chemistry are found in a fan-like spread, analysts trace the vector upstream or up ice to identify probable source zones. These are then subject to geophysical surveys, magnetic, electromagnetic, and gravity, looking for pipe-shaped anomalies consistent with buried kimberlite or lamproite bodies. Field testing follows. Auger drilling, trenching, or bulk sampling provides the physical rock for confirmation. Each step costs more, so samples must be prioritized by data, concentration density, indicator chemistry, and geophysical signature. In Canada, bulk sampling often involves extracting several hundred tons of kimberlite to recover a handful of diamonds, enough to establish grade and potential commercial viability. The benefit of following this system isn't just consistency, it's credibility. Lab-tested indicator minerals, mapped dispersion trains, and geophysical overlays create a data package strong enough for exploration permits, investor interest, and eventual mine development. Whether you're a hobbyist or an explorer, aligning your work with these methods boosts not just your hit rate, but your legitimacy in any downstream sale or partnership. Smaller-scale fieldwork can adapt this model. Instead of a nationwide grid, apply the same logic to a local drainage. Instead of electron microprobes, rely on sieving, magnet sorting, hardness testing, and hand lens analysis, but keep detailed notes. The system scales because the logic holds. Find the right minerals in the right place with the right traits and follow them to their source. The same method that uncovers billion-dollar diamond fields in the Canadian Shield falls flat in the lush plains of central China or the sedimentary basins of the U.S. Midwest. It's not for lack of skill. It's because geology sets the rules. Knowing where this method works and where it doesn't can save years of effort and thousands in wasted assays. Start with where it thrives. The classic terrains for diamond exploration are stable cratons, ancient, unmoving sections of continental crust. These regions, such as the Kopval Craton, South Africa, Slave Craton, Canada, and Siberian Craton, Russia, are old enough and deep enough to have generated diamond-forming conditions. More importantly, they host the vertical volcanic structures, kimberlite and lamproite pipes, that serve as conduits for diamonds to reach the surface. In cratonic terrains that experience glaciation, like much of Canada and Scandinavia, ice sheets scrape through these pipes and scattered mineral-rich debris across hundreds of kilometers. This glacial till often blankets terrain, hiding the pipes but preserving a record of their erosion. It's here that indicator mineral trains shine brightest, pointing prospectors back towards source zones with remarkable accuracy. In contrast, arid or tropical cratons, such as those in Western Australia or Brazil, lack glacial processes but offer something else: deeply weathered surfaces. Kimberlite weathers faster than surrounding rock, creating subtle depressions, or ferrocrete caps visible in satellite imagery. Here, drainage-based indicator sampling still works, but it requires tight timing. Wet seasons concentrate indicators. Dry seasons expose host rocks. Now, where it fails: in flat, young sedimentary basins, like the Gulf Coast of the US or much of Central Europe, there's no mantle-rooted volcanic plumbing, and thus no primary diamond deposits. Even alluvial diamonds here are rare and poorly sourced, having been transported from distant terrains long since eroded. Indicator mineral sampling in such regions turns up scattered heavies, but without a pipeline source, the trail goes cold. Volcanically active zones can be misleading too. Basaltic terrains may contain dense black sands, magnetite, and garnet-like minerals that mimic kimberlitic indicators but bear no connection to diamonds. In the Philippines, Hawaii, and parts of Indonesia, black sand beaches yield ilmenite-rich concentrates that lead nowhere for diamond prospecting. The host rock simply isn't deep enough or of the right chemistry. One surprising middle ground? India. Though long considered exhausted, some regions within the Darwar Craton and Bundelkhand Craton still host viable lamproite and ultramafic dikes. But here, the pipes are narrow and deeply weathered, often hidden beneath agricultural land or river terraces. Indicator sampling works, but only if adapted for subtler expression. Garnets in termite mounds, ilmenite in stream banks, chromite in paddy soils. Understanding your terrain isn't just about rocks, it's about process. Does the region have a history of high-pressure ultramafic volcanism? Is it old enough to have hosted diamond growth, but not so eroded that pipes are gone? Was there glaciation or significant fluvial reworking? These questions guide whether you grid or walk away. Yet even in the best terrain, not all diamonds are equal, and the indicators that signal any diamond aren't necessarily the ones that signal valuable ones. That's why in the next topic, we'll go deeper, not just into what the indicators are, but what they mean when they cluster in specific ways, pointing to large, cuttable stones versus industrial grit. Not all indicator minerals are created equal. The presence of pyrope, garnet, or ilmenite in a stream sample suggests potential. But when those minerals appear in the right ratios, chemistries, and spatial patterns, they hint at something more. A diamond pipeline not just rich in quantity, but in quality. The difference between a deposit that yields abrasive-grade microdiamonds and one that produces gem quality, cuttable stones, often lies in the company they keep underground. Start with the garnet suite. Pyrope garnets are broadly classified by their chromium content, but two subtypes stand out: G9 and G10. G10 garnets are low in calcium and high in chromium, a chemical signature found in the high-pressure stability field where diamonds form. Their presence in a kimberlite matrix is a strong predictor of gem-quality diamond potential. G9 garnets, slightly higher in calcium, are still favorable, but more commonly associate with smaller or lower-quality stones. When G10s are found in abundance, especially with angular, unabraded grains, they're often traced back to a relatively uneroded kimberlite source. The freshness of the garnets matters. If they retain sharp edges, the transport distance was short, and the source pipe may still be intact. Combine this with chromite grains showing a high CR, Fe ratio, and ilmenite with low oxidation levels, and you've got a mineralogical stack that practically begs for confirmation sampling. But there's more. Chrome diopside, though less talked about, is a powerful vectoring tool. It's a pale to deep green monoclinic crystal common in diamond-bearing peridotites. Its presence in significant quantities, especially alongside G10 garnets, often correlates with larger stone sizes. Some of the best-producing pipes in Russia and South Africa show high chrome diopside counts in their indicator trains. Next comes mineral collocation. If your pan or sieve turns up just garnet, it's a weak signal. But garnet plus ilmenite plus chromite in the same sample, especially if supported by clinopyroxene or spinel, suggests erosion from a deep, composite kimberlite system. These systems often tap multiple mantle layers and are more likely to produce larger stones due to longer ascent times and pressure variation along the conduit. Then there's grain morphology. Rounded grains signal long transport or reworking, likely from an older, depleted pipe. Angular, zoned grains suggest fresh erosion and proximity to the source. Inclusion studies of such grains in lab settings often correlate them with type Ia or IIA diamonds, the latter being nitrogen-free, extremely rare, and capable of fetching premiums on the open market, especially in the blue and pink spectrum. Another clue is mineral zoning across your grid. If high-quality indicators cluster tightly in a 50-meter radius but vanish outside it, you may be close to a pipe throat or diatry margin. If they stretch out in a plume or fan over hundreds of meters, the source is farther upstream or up ice. Recognizing these patterns is critical when deciding where to dig, trench, or assay. Still, not all kimberlites are created equal. Some pipes contain diamonds, but of such low quality they aren't worth mining. That's why confirming mineral associations is only half the equation. The other half is knowing what not to waste time on. Because safety, legality, and practical limits on access can turn a good lead into a dead end. Next, we'll take a hard look at those boundaries. Flood risk, slopes, permitting, and the overlooked hazards that separate safe fieldwork from reckless exposure. The best indicators often show up in the worst places. Steep drainages, remote outcrops, or stream beds that flash flood without warning. In the hunt for diamond-bearing rock, the danger isn't just misidentifying minerals. It's underestimating terrain, weather, and legal boundaries. Many promising sites have been lost not to geology, but to avoidable risk and access violations. Start with slopes. Indicator-rich nodules often weather out of vertical faces or colluvial deposits. Loose, unstable hillsides prone to sudden slides. When digging or sampling along such slopes, the first test is not mineral. It's structural. Does the face show recent shearing, cracking, or vegetative collapse? If so, set your work zone downhill, on stable benches, and avoid undercutting any overhang. Use a hand auger or trenching tool with a long handle to reduce direct exposure. In stream systems, the most productive areas are often also the most hazardous. Inside bends, gravel bars, and low-lying terraces concentrate heavies. But these are exactly where water piles up during sudden rains. A dry channel can become a torrent in minutes if upstream rainfall exceeds runoff capacity. Before panning or sieving in such zones, check weather forecasts, note cloud buildup in the catchment, and identify exit routes. Always sample with someone aware of your location, especially if working in a seasonal or monsoon-prone environment. Then there's the legal side. In many regions, collecting samples from private land or protected areas, even if only float, rock, or stream sediment, requires explicit permission. Mineral rights are often split from land rights, particularly in countries with legacy mining laws like Australia, South Africa, or India. Sampling without the correct license, even for academic or amateur purposes, can result in confiscation or legal action. This is especially true in declared kimberlite fields or known historical workings. Some governments publish mineral tenure maps and permit databases. Before targeting a promising site, check whether it lies within a claim, lease, or exploration block. In many places, such as Canada's Northwest Territories or Botswana's Orapa District, sampling within a licensed concession requires written permission from the leaseholder. In contrast, some U.S. states allow recreational sampling on certain public lands, provided no mechanical excavation occurs. Permits aside, ethical sampling is also about minimal disturbance. Avoid draining ponds or diverting creeks, even temporarily. Use tools that leave no permanent marks, such as trowels, batti pans, or hand sieves, and pack out all waste. If you open a trench or scrape a face, backfill and camouflage the site before departure. This isn't just good stewardship. It reduces the chance of public backlash or future access restrictions. Wildlife is another overlooked variable. Remote sampling zones often lie within animal corridors or protected habitats. Elephants, bears, snakes, or even territorial birds can turn a productive grid into a no-go zone. Carry deterrents appropriate to your region, and avoid working at dusk or dawn when movement is highest. In known predator zones, don't work alone. Fieldwork is exhilarating when you strike promising ground. But without awareness of environmental, legal, and logistical factors, even the best finds become liabilities. The smarter approach is to build safety and legality into your workflow, just like you would your testing suite. At some point, the evidence on your field table outweighs the doubt. Multiple samples across your grid consistently produce G10 garnets, ilmenite grains with low oxidation, and dense, non-conductive blue inclusions that pass thermal tests. You've mapped the dispersion vector, ruled out false positives, and verified rock types consistent with diamond pipes. Now comes the inflection point. When do you go beyond field tests and invest in full lab verification? The trigger is repeatability. If 3 or more grid cells spaced tens of meters apart yield the same indicator suite, especially with at least one suspected diamond inclusion, it's time to scale up. But not with guesswork. Your next move should be a controlled sampling and test plan, designed to minimize cost while maximizing certainty. Start with bulk sample selection. Identify the cell or stream segment with the highest indicator concentration. From this, extract 50 to 100 kilograms of material if allowed by law. This could be heavy mineral concentrate, float material, or matrix rock from a fresh exposure. The goal is to generate a statistically significant sample, something large enough that, if diamonds are present, they won't be missed due to low volume. Then select the lab. Not all gemological labs are suitable. You need one with experience in rough diamond verification and heavy mineral separations. Institutions like the Geological Survey of Canada, GSC, Saskatchewan Research Council, SRC, or private labs like SGS and Overburden Drilling Management, ODM, offer services tailored to diamond exploration. For rough validation, ask for heavy mineral separation using dense media, SG greater than 3.3, indicator mineral classification with microprobe analysis, diamond recovery via caustic fusion or X-ray sorting, specific gravity and refractive index testing on suspect grains, Raman spectroscopy to confirm crystal structure. These tests go beyond what's possible in the field. Caustic fusion, in particular, is the gold standard for extracting microdiamonds from kimberlite or lamproite. The process dissolves the silicate matrix in a hot sodium hydroxide bath, leaving behind diamonds and other insolubles for microscopic inspection. Cost is non-trivial. Expect a few hundred to a few $1,000s per batch, depending on sample size and tests requested. But here's the logic. One confirmed microdiamond, especially in a chemically favorable matrix, can validate the entire search zone. If that diamond is a transparent octahedron with no inclusions, even better. That speaks not only to presence, but quality. If a stone is recovered and passes thermal, electrical, and optical tests, confirming it as diamond, the next step is certification. For this, partner with an accredited gemological lab like GIA, IGI, or HRD. Though these institutions focus on cut gems, they also issue origin and rough diamond reports upon request, especially for scientific or legal purposes. That report becomes your leverage. With it, you can approach cutters, investors, or license holders. You can negotiate access to larger concessions, raise funds for further sampling, or enter joint ventures. The data trail, from field sample to certified rough, becomes your proof of credibility. A rough blue diamond pulled from the earth is not a final product. It's a potential, and how that potential is realized depends entirely on market context. Clarity, size, cut potential, and, critically, provenance. A stone worth $5,000 in one scenario could command $200,000 in another, simply based on where it was found, how it was handled, and who ends up cutting it. First, the grading pyramid. Diamonds are valued on the traditional 4CS, carat, color, clarity, and cut. But in rough form, cut potential replaces cut. A well-shaped octahedral crystal over 1 carat with few visible inclusions and strong transparency is prized. If it's blue, especially with even coloration and no surface staining, it enters a much narrower, high-value tier. Type IIB diamonds, boron-colored, can command extreme premiums due to rarity and collector demand. But value isn't linear. A 0.50 carat pale blue rough might sell for $2,000 to $3,000. The same stone at 1.2 carats with clean faces and strong blue saturation could fetch $20,000 to $40,000. At 2 carats or more, especially with certification, private sale or auction values can exceed $100,000. Exceptional blues, those with vivid saturation and type IIB classification, can rise exponentially, especially when cut well. The 14.62 carat Oppenheimer blue, once cut, sold for over $50 million. Its rough value would have been high, but nowhere near that figure. Provenance matters. A stone traced to a well-known field, like Cullinan, South Africa, Argyle, Australia, or Lullo, Angola, often carries a built-in premium due to established reputation. But lesser-known or new fields can also boost value if evidence shows consistency, legality, and gem quality potential. That's why documentation is critical. Photos of the in-situ rock, grid coordinates, if shareable, lab reports confirming matrix type, and indicator suites build the story that supports your asking price. If your find comes from a country with strict export laws, Botswana, Angola, Namibia, you must declare and often sell through government channels. In other regions, like Canada or parts of the US, you may retain ownership, but must still follow customs and valuation processes if exporting. Working with a licensed gem trader or cutter with export clearance is the safest route. There's also the question of cutting. Rough stones are almost always discounted due to uncertainty. Cutters assume risk. Flaws may emerge, yield may be low, or color may fade under polishing. If you want top dollar, you may consider partnering with a reputable cutter who offers a share model. They cut the stone at cost, and you split the final sale price based on agreed terms. This ensures proper treatment and opens access to high-end buyers. Alternatively, you may choose to sell rough to a collector or dealer. In this case, certification from GIA or IGI, combined with microprobe analysis and Raman confirmation, forms the basis of negotiation. Beware buyers who downplay flaws to depress price, or who pressure for immediate sale without third-party valuation. Always get at least 2 independent opinions before parting with a stone above $10,000. But what if the buyer is dishonest, or the market flooded with similar-looking stones? That's when scams and underpricing begin to erode value from even the most promising finds. In the next topic, We'll uncover how these traps work, what red flags to watch for, and how to protect your discovery from becoming someone else's windfall. The scam begins before you even know you're holding a diamond. It starts with a soft push. A local buyer offers you a few $100s for a rough stone that might be topaz. Another steps in with a better offer, but says it needs cutting first. Or worse, they dismiss it altogether as just glass, banking on your inexperience. These are classic underpricing tactics, and they happen worldwide. Without knowledge, even a 5-figure stone can be sold for the price of a night's lodging. One of the most common traps is simulated certification. Some buyers produce printed gem reports that appear legitimate, but lack verifiable serial numbers or use vague terms like diamond simulant or sapphire-type material. Others offer on-the-spot testing with cheap devices calibrated to produce no result, especially if the stone is dirty or irregular in shape. Their goal isn't to confirm, it's to shake your confidence. Dyed quartz and treated topaz are often passed off as low-grade blue diamonds in field markets. These stones may test positive under thermal conductivity, show internal veils under magnification, or even fluoresce faintly under UV. But under Raman spectroscopy or refractive index testing, they fail instantly. Unfortunately, these lab tests cost money, and that costs dealers many finders from verifying what they hold. Then there are synthetic blue diamonds, CVD, chemical vapor deposition, or HPHD, high pressure, high temperature, which are now common in the global gem market. These stones are real diamonds but lab-grown. Their market value is drastically lower, and once mixed into parcels or misrepresented in rough form, they can destroy confidence in an entire batch. Even experienced buyers have been caught off guard by synthetic material with natural-looking inclusions. The only reliable defense is documentation. If your find has passed thermal, UV, SG, and electrical tests, and especially if Raman or lab confirmation exists, it must be accompanied by chain of custody notes. Who found it, where, with what method, and when? Each piece of metadata narrows room for dispute. Even simple photos, taken during extraction or in grid context, can provide powerful proof in resale. Negotiation ethics are another factor. Some buyers operate as intermediate validators, claiming to offer access to international dealers. Their model: offer a fraction of real value for immediate liquidity, then flip the stone at full market rate. If you suspect this, better to wait for a proper platform. Online gem marketplaces, auction previews, or in-person gem shows, than to sell under duress or doubt. One underused resource: independent gemologists. For a few $100s, many will issue non-binding but expert assessments of rough stones, including recommendations for next steps. Some specialize in rough, uncut diamonds and can even connect you with cutters or trusted dealers who avoid first-tier scams. The worst-case scenario is losing a real diamond to a fabricated dispute. A buyer claims your stone was switched, cracked, or turned out synthetic after they've taken possession. Without signed records or proper receipts, you're out of luck. That's why every exchange, no matter how informal, should include written terms, photos, and ID verification if significant value is involved. Despite these risks, the legitimate path to sale still exists. It's just narrower and slower than most expect. But once you've verified your find and protected your position, the payoff is real. And in the next topic, we'll see how a simple side-by-side test suite can settle doubt forever and establish what you've truly uncovered. Doubt vanishes in the face of repeatable evidence. The blue crystal, set side by side with a known lab diamond, a sapphire, and a piece of synthetic spinel, tells its own story under the lens, the probe, and the scale. It's not about what you hope it is. It's about what the tests prove it is. And when every result aligns with known natural diamond signatures, there's no room left for guessing. The process begins with a clean surface. A tiny window is polished on one face of the suspected diamond using fine diamond paste or 6 sandpaper, 9 on the Mohs scale. This gives a clear spot for measurement, free of dirt, oxidation, or weathered crust. The first test is thermal conductivity. Using a calibrated probe, the stone responds instantly, reading in the diamond zone. Fast heat dissipation, high thermal response. For control, a moissanite sample is tested next. Also registers, but then the electrical conductivity probe comes in. Moissanite conducts. The test stone does not. One imposter ruled out. Each option has implications. Tax, export laws, cutting jurisdiction, and resale limitations. If you plan to cross borders with a stone, a Kimberlite process certificate may be required to prove it's conflict-free. Even for rough under 1 carat. Some countries restrict diamond export altogether. Others require customs declaration and valuation reports. Always research the legal framework before committing to any route. But one thing's certain, you're no longer speculating. You're choosing from a position of verified value, backed by science and documentation. That's a rare place to stand in gem prospecting,